Here we are in activity 2. In this activity, you will investigate the relationships between complementary trig functions for, we've seen these before, 30, 60, 90s, and 45, 45, 90 triangles. Those are the special right triangles. You have to be an expert at those. For now, for Algebra 2, for Pre-Calc Trig, for the Smarter Balanced Assessment, you have to be an expert at the relationships in these triangles. So, pay attention. Use the complementary angle relationships, your knowledge of the side relationships of special right triangles, and the Pythagorean theorem to complete the chart with the numeric ratios. We want exact answers. For each triangle. And believe me, this right here is you must know this page. And maybe not immediately, but eventually. This will be like a recurring theme in the next 4 years of calculus or mathematics for you, up to calculus. Reference angle. From 30 degrees in the 30, 60, 90 triangle, if we're going to be referencing 30 degrees, then our hypotenuse, remember label theta, identify that first, then the hypotenuse, then the opposite, and then the adjacent side. So theta at 30 degrees, the hypotenuse, the opposite side, and the adjacent side, in that order. What you should also know is the ratios of the sides of special right triangles. So if you haven't watched that video yet, let me create that for you right now. In a 30, 60, 90 triangle, let's go this way, this way, this way, 30 degrees, 90-degree corner in the box. Maybe this is notes on a scratch paper, and then 60 degrees up here. And also I'm going to make my window much bigger. Okay, so here we are. The hypotenuse is always going to be twice as big as the side opposite the 30-degree angle. So there's a equilateral triangle explanation for why this is true. Go back and watch one of my YouTube shorts. Go back and see those ones, but this is like the tutorial in the moment of this. So if we know, because of that stuff in the past, then 1 here and 2 there, help us find the side length that's missing with the Pythagorean theorem. So a squared plus b squared equals c squared. That's a, that's b, that's c. 1 squared plus b squared equals 2 squared. So to solve for b, we're going to need to, square things. We're going to subtract, and we're going to last of all square roots. 1 squared is 1. 2 squared is 4. 4, take away 1. That's the squared value of that side length. The Greeks knew this. The Romans followed off the Greeks. The Babylonians knew it thousands of years before. That if you literally construct a square out here on the edges of this right triangle, these two squares will add up to that one. So we're doing that math right here. In essence, there is a square with area 3 off of that side length. I know I'm doing the algebra of it all, but the Greeks were very good at shapes and shape logic. If we square root, that'll cancel the square, and it'll tell us the side of the square. B is square root 3. Take this, put it on your paper. So 1, 2, square root 3. Let's go back. Okay. So not only do we have this relationship with 30, 60, 90 triangles, we also have a similar one with 45, 45, 90. So here's a 45, 45 triangle, 90 degrees in the corner. Of course, if that angle is 45, its complement is 45. So we should be able to do, 90 minus 45 to figure out that angle up there. This is actually like taking a square and folding that square in half diagonally. So if you do that, then the sides of the square are the same. But what we don't have in this relationship of a square folded in half is the hypotenuse. We do know the two side lengths that match, so there's a squared plus b squared. Or if you like how it matched from over here, 1 squared plus b squared would be the same structure. But the thing we don't know is the value of c. So with Pythagorean theorem, 1 squared plus 1 squared equals c squared. 1 squared and 1 squared make 2. And like the Greeks knew, if you created a square off of that side length, it would have an area of 2. If you created squares off of these side lengths, they'd have areas of 1 and 1. And when you add them together, it would add up to 2. It's called the windmill diagram. Now, to figure out the length of c, we square root both sides. So the square root cancels c squared, leaving us with c. And then square root of 2 is not 1. Students will say this all the time. Equals 1, right? No. Square root does not mean divide. It means what number times itself equals 2. And good luck getting an exact answer. So if we write it, we could write it just like that. Now, if you need to know, because we should know, you just go, hey, Siri, what's the square root of 2?
That would be approximately 1.4142.
Okay. Hey, Siri, what's the square root of 3?
The answer is approximately 1.732.
You heard it say approximately though, right? So that's the key thing is these are not exact answer. No, these are exact answers. What you do with the calculator to get a decimal of 1.4142, that's an approximate. But let's take these angle relationships and put them here. 1, 1, square root 2. Those have to be memorized or replicable. Reproducible? Okay, back into it. The sine of angle 30 degrees, which is here with the opposite and hypotenuse, is 1/2. The cosine of 30 degrees, so cosine is adjacent hypotenuse, is root 3 divided by 2. The tangent is opposite over adjacent, so opposite over adjacent would be 1 over square root 3. The cosecant would be the reciprocal of sine. So sine, when you do its reciprocal, is 2 over 1, which I should just write a 2 there, but I want you to see the reciprocal nature. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So there we go. We have them, our 6 ratios from angle B. Now we flip this around and we go over, different pen time, we go over to angle A because that's 60 degrees. All right, remember, those two angles in the triangle are complementary. So if one of them is 60, the other one is 30 and vice versa. This is our new reference angle. The hypotenuse stays the same, but this is now the opposite side, and this is now the adjacent side. And if we start using sines, cosines, and tangents now, you'll see that the sine of angle 60 is root 3 over 2. The cosine of angle 60 is 1 over 2. This is that same relationship across the complementary angles. The tangent of 60 is root 3 over 1. And then we're just seeing the flip. In fact, I'm going to use the structure from the previous activity to just acknowledge crisscross applesauce. So there it is, root 2, right? 2 over root 3, 2 over 1, 1 over root 3. Go back and check that it does match what's happening on in that triangle. Okay, other special right triangle. 45 degrees. Since both of these are 45 degrees, it doesn't matter where you say your your reference angle is. They're both 45 because the hypotenuse will always be the same, but the adjacent side and opposite side, they're both equal to 1. So the sine of 45 degrees, let's say its reference angle is down here, hypotenuse, opposite, adjacent side, kind of like a backwards clock. We have 45 degrees, so we have 1 over square root 2. And then we have cosine, so 1 over square root 2. For tangent, we have 1 over 1, which of course equals 1. Cosecant and secant are just reciprocals of those two fractions. So root 2 over 1, root 2 over 1, and cotangent is the reciprocal of tangent, so 1 over 1. 45, 90 degree triangles are so nice. Okay, question 2. Trafalgar Square is a tourist attraction located in London, England. The name commemorates the Battle of Trafalgar in 1805, a British naval victory of the Napoleonic Wars over France. Use a trigonometric function to solve the dimensions of Trafalgar Square. So, we have this diagonal measurement, and we need to know the side lengths. Use trigonometric functions to solve the dimensions of Trafalgar Square. So this is a 45-degree angle here because it's a square, and this line is the hypotenuse. So one of the nice things that we have from this table is we have a ratio that uses hypotenuse, 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 hypotenuse. And if we need to know a side of the square, we could say S meters, and we could use sine. In other words, in this triangle, we have a 45-degree angle. So the sine of 45 degrees would be opposite over hypotenuse, 24/200 square root. But we also know from the table up above that that equals 1 over the square root of 2. So to solve for S, the side of the square, we just need to solve this proportion to figure out the value of S. By the way, it is S. Sometimes I add little feet and a head on the S to make it look more like an S than a 5. Multiply both sides by the square root of 24,200. So S will equal 24,200. The square root of 24,200 divided by the square root of 2. Hey Siri, what's the square root of 24,200 divided by the square root of 2?
The square root of 24,200 divided by square root of 2 is approximately 109.9999.
110 meters. Hey Siri, how big is Trafalgar Square in London? Oh, look it up yourself. Okay, the diagonal of a square forms which type of triangle? A 45, 45, 90 triangle. How is the Pythagorean theorem used to solve for the length of the hypotenuse? Little review. How did we get square root of 2 for our hypotenuse? Thank you for watching, liking, commenting, and subscribing. I'm going to leave those questions lingering in your mind as you think about them and come up with an answer for them. And I'll see you in the next episode.